Okay, so in this session, session 2, it's about an hour long, and I'm going to be talking about DFT. So Corey gave a nice introduction to DFT, and so we actually saw that it could be somewhat tedious to create all of those postcard geometry files, this incars, the K-points file, and things like that. And so now this is where aflow comes in, and aflow can essentially help us to automate this process. And so this session is DFT plus aflow, an automatic framework for materials discovery. And so Cormac already went over this slide briefly. And so this is the overall workflow of aflow. So aflow is a C++ GNU code that essentially interfaces with a DFT code. And in particular, we've been working with VASP. And so we start typically with an input file known as the aflow.in. And so this contains all of the information that we need to run a VASP calculation. So it contains information for the postcar, the incar, the K-points, and the potcar. And so instead of 4 input files, we're just dealing with 1, and aflow will generate these files automatically. And so this is a great advantage compared to the previous session where we had to create all of these files by hand. And for some of the files, the incar, Corey actually gave us these files, so it would have been a lot harder if we had to build these files by hand. And so with this one input file, we can run density functional theory codes, or in particular VASP. And so typically we've been only running one VASP calculation at a time. However, aflow can submit multiple DFT jobs, or essentially an ensemble of density functional theory codes. And so this is particularly important for thermomechanical properties, also to model disordered structures. And so this is a great advantage to use aflow. In addition, we won't really highlight here today, but sometimes DFT or VASP may give you an error. So there may be something wrong with either the geometry or some type of common VASP output error. And so aflow can automatically handle some of these errors. And so it'll actually reformat or basically change certain parameters in the aflow.in and then resubmit the calculation. So again, this is highly automatic. And so once we've had a successful run, then we can do some post-processing. So we have many, many different modules and codes that we'll see today that can extract certain properties such as electronic, thermal, and elastic. And then finally, all of this, for our purposes, is stored in our openly available aflow.org repository for us to disseminate to the rest of the scientific community. And so actually, we're just going to go ahead and jump right into it. And we're actually going to go step by step on how to create this aflow.in file. So I'm going to go ahead and exit the presentation. And I think I'm going to swap in for the PDF just so it's a little easier to see. Okay. So I'm going to have both open side by side. And so we're going to be using the terminal a lot for this session. And so some of you may be unfamiliar with some of the commands. So I'm going to try to go very slowly, and I'll try to explain everything that I'm doing. But again, if you have questions, feel free to message us in the chat. Okay, so we'll go to the portal, and we're going to open up the terminal. So you can either right click and open terminal. I already have one open, so I'm going to open this, and I've tried to zoom in quite a bit. Okay, so first we need to navigate to the correct directory. So that's with the change directory command. So if we run cd space, and then if you do tab, you can see some of the directories that are available. So we need to go to the desktop. If we hit tab again, we get aflow day, and we're still in day 1. So hit tab again. And then now we're going to be going into the O2 aflow DFT. So we'll type O2 _ aflow _ DFT, and then let's hit enter, and we're going to navigate into this directory. So to see what the contents of the directory, we type ls, enter, and we see that there's 4 directories that we're going to be working with. So to go in the directory, we do cd 1 _ aflow in. And hit enter. And then if we do ls to see the contents of the directory, we see that we have a postcard and a readme. So the readme is going to tell us a little more information on what we're doing. And so I'm going to use the command cat or concatenate. So cat, then readme, and hit enter. And so this is going to tell us what we're doing. So I'll highlight it here. Hopefully it's a little easier to see. So we're going to create this, we're going to take this postcar, which happens to be the rock salt sodium chloride, and we're going to convert it into the single aflow in input file. So we're going to do that now. So that's the first step. So ls. And so to do this, to build an aflow in, so again, we're looking at the slides here. To build an aflow in from an existing postcar, you can run the aflow command, so which is aflow minus postcar to aflow in, and you can redirect the postcar. So there's two ways you can do this. You can either cat the postcar, so I'll do that first. So cat postcar, and then I think we mentioned in the last module, we need to pipe. So typically I think that's shift and slash for me. So the pipe, and then we do aflow minus postcar to aflow in. Make sure you spell it right, and then hit enter, and it's going to create some output. Alternatively, you can redirect the geometry file by doing this instead, which we have shown here. So we can do aflow minus postcar to aflow in, and then we can direct a certain file. So we're going to do postcar. And in this case, we're going to direct the output to a particular file, which we call aflow in. So hopefully that's not too confusing. So, but basically, you'll type this command and hit enter. So if everyone does that, you should see when you do ls that we've created this file here. So let's take a look and see what's in that file. Or actually, before we do that, we're going to actually create even more input files. So if we do ls and then cat readme. So first, one way of creating the aflow in is to take a particular postcar. So maybe you grabbed it from an online repository and you can convert it to the aflow in. But aflow does have some built-in structured prototypes already in the software that you can generate. And so I'm going to be talking about this a lot more when we discuss prototypes. So I'm going to give you a little taste here. So here, what we want to do is we want to generate the Heuser structure. And so this is a prototype that's already hard-coded into the aflow software. So to generate this structure, we would type aflow minus aflow underscore proto equals. And so now we need a designator or a label for this particular prototype. And so in this case, it's given here. So it's T0001 dot A to B. And then we want to decorate it with certain elements. So in this case, we want to create this particular compound. And so we need to specify the elements in alphabetic order. So here we do CU. And each element is colon separated. So we do CU colon TI colon ZN. And so if we run this, we'll actually before that, I forgot that we need to load the module. So to do that now, so we'll do module load aflow T. There we go. We needed that. And then also we're going to load the GCC module for later. So module load GCC. There we go. Load. It looks like it's not popping up. Looks like I don't have it. I'm not sure why. I don't think we need it yet. So actually forget about that for now. Okay, sorry about that. Okay, so but we should be able to create this command. So I'm going to type it again. So it's aflow. Okay, so aflow minus aflow underscore proto equals T0001 dot A to B C colon CU TI ZN. There we go. Okay, so now what this command did is it created a multiple subdirectories. So we see that we have this aflow data, and then within this we have basically the alloy system that we made. And you'll notice that we have some extra characters here. And so this corresponds to the pseudopotential information. So this says that copper and then PV, and so this says that we're treating the p electrons as valence. And so if you go to any VASP manual, you should be able to see the different potential information. And you can look up this to see what these pseudopotentials are doing. So in addition to this, we can create multiple prototypes from a single command. So that's given here. So if we want to do this, we do aflow --aflow _ proto equals T0001.A2BC. And now let's say we want to use another prototype. So we want to use this TFCC. So we would put a comma and then TFCC 001.ABC. And so again, these are labels that I'll talk about tomorrow morning. But for now, you kind of just have to take my word for it. And so let's say that we also want to decorate with different elements, with multiple different combinations. So to do this, we put colon, and let me make sure I'm typing in the right place, colon. And so we want to decorate the first site with silver or gold or copper or iron. And then we put a colon for site B. And so there we want to decorate with either manganese or titanium. And we put colon. And then for the last site, we want all zinc. And so if we hit enter, we actually see that we create multiple files. And so we can see that in one command, we've been able to generate almost 15 different structures with one command. And so, so there are many different ways that you can create multiple structures. So here's another command. And so let's actually go into one of these directories. So to do this, we'll hit ls. So we can see that we have this aflow data directory. And so we do cd aflow data, hit enter. And then we should see that we have these different subdirectories for the different alloy systems. And so to navigate in here, we do cd, and let's go to the first one. So silver, manganese, _ PV, ZN. And we hit enter. And we see that there were two prototypes. So this is the prototype layer. And so for this particular alloy system, we generated two structures. Sorry, it looks a little fuzzy here in the terminal. But if we navigate to this first one, so T0001.A2BC, hit enter. And in each of these subdirectories, there's an aflow.in file. And so now let's actually see what's in the aflow.in file. So supposedly, there should be enough information to perform a VASP run. So to look in the file, we're going to use vim. So to do this, we do vi aflow.in. And we'll hit enter. And so it looks like the spacing's a little off just because we're zoomed in so much. And so if you're a Vim person, or if you're not, we're gonna run this command. So if you put colon and then put set no wrap and hit enter, then basically we get nicer formatting so we're not wrapping around all of the lines that are not shown. Okay. So then I'm going to use the arrows to navigate, and we'll go through what the aflow.in file looks like. So here we see some collaborator information. This is by far not exhaustive, and so we should update this, but these are some of the collaborators that have worked with aflow. It tells us who generated the file. So in this case, my ID number is CMSAS3, and so it'll probably be different for everyone else. We have the system name. So this tells us basically that we're running this particular alloy system and with this prototype structure. And then we have information on some certain compression. So we're going to use XZ compression anytime we compress a file. we've already specified the VASP binary. So there's the VASP standard. So when we run VASP, it's going to call this particular binary. If we scroll down, there's some MPI information. So if you're running multiple processors, you may want to specify the message processing interface options. And so those are given here. And here below, we have different modules. And so here we can see we have symmetry, we have neighbors, aflow neighbors. And so if we want to run these modules, they need to be uncommented. So you'll notice that here, this line is not commented. However, some lines contain a hashtag or £, and these indicate that these are commented out. And so when we run aflow, it'll ignore these lines. And so with aflow, you can run multiple analyses at once. So we're going to run symmetry, for instance. We're going to ignore this neighbor calculator. And then, as we've said, there are different modules. For instance, if we wanted to run a phonon calculation. So this is designated by aflow APL calc, but we can see that it's commented out. But later on, I think in session 9, Marco's going to be talking about phonons. And he'll talk about all of these options that are shown. Scroll down some more. There's another module, so aflow QHA for the quasi-harmonic approximation. So in this case, APL, we typically use the harmonic approximation, and then QHA is the quasi-harmonic, so we're essentially building on this theory. And then there's also AAPL, and so this is the anharmonic automatic phonon library. And so this includes higher order terms. And again, here are all the options. Cormac's going to be talking about thermomechanical properties. So this is the aflow Gibbs library and all of the relevant parameters. If we scroll down some more, AEL, the aflow elastic lib library. And again, the different parameters. And then finally, for a normal VASP calculation, we see these VASP run. And so here you specify the relaxation. And in this case, this says that we're going to be doing 2 relaxations. And I'll talk about why there's 2 here in the next few slides. But then again, here we see a variety of different input parameters. And so some of these correspond to maybe certain things in the in-car. We see that maybe we want to turn spin on, automatically specify the magnetic moment, relax with respect to the energies as opposed to the forces in the DFT relaxation, the precision, and then also the algorithm type. And so these are all options that are given in the aflow in file. And if we scroll down, then we see here that if you wanted to modify certain things in the in-car by hand, then you could specify that here. Corey talked about the K points. And so here is specifying some of the K point information, and I'll talk about exactly what these mean on the next few slides. And then finally, at the bottom, we have the geometry file. So this is the Heuser postcar, and we can see that it's been inserted towards the bottom of the file. And what's nice is that we didn't have to generate this by hand. And so again, this is where the aflow prototype encyclopedia really comes into play. And then at the very bottom, we have the pseudopotential information. And so this was grabbed from the pot car, where this will help us to specify which pot car we'll be using for the calculation. So this is the aflow in file. And so this was generated automatically with one command. And so a VI reminder, so we're in this file right now, and to leave it, we need to hit colon and then Q. So this will allow us to exit. So I guess feel free to ask any questions in the chat on the aflow in, but I'm going to be talking about some of the parameters a little more in detail. And so to do this, you may be wondering, where did these parameters come from? How did we come up with these parameters? And so if you're following along on the slides, we've provided a paper, which is given by this DOI, and this is the aflow standards paper. And so this specifies in great detail the different parameter choices that we've chosen for the default aflow in settings. And so if you're on the portal, we've given you this paper. So again, if you go to the aflow day 1 directory, and if you go to aflow, it's in this main directory here. And so if you type on aflow standards, it should come up. So, but I'm actually going to use the one that's on my desktop just because I think it's a little easier to see. And so in this paper, feel free to look at it on your own, but you can see that this is a paper that we wrote a few years ago. And so this details all of the parameter rationale for what's in the aflow in. And so a few things that I want to point out are the number of relaxations. So in general, we want to perform relaxations at a high throughput level, and we want to make sure that they're sufficiently relaxed. And we need, as Corey mentioned, for density of state calculations, we want to make sure that we have a static calculation. And then if we're running the electronic band structure, we want to have a bands. And so we have a particular procedure to perform these step by step. And so in general, we typically have the following sequence. So we'll run one relaxation. Let me zoom in maybe just a little bit just to make sure people can see. So the sequence is to run one relaxation, and then we run another, essentially as an annealing type step. And then once it's sufficiently relaxed, we run a static calculation. And then if we want the band structure information, we would run a subsequent band structure calculation. And so that's the typical set of steps. And so here we talk about more of the standard parameter set. And here, one thing I want to mention is the K-point sampling. And so Corey mentioned the different K-point meshes. So in particular, Monco's PAT or gamma-centered. And so in one of the exercises, we had to determine basically how many K-points or a K-point grid, whether it was 10 by 10 by 10, 20 by 20 by 20, what was sufficient for us to get convergence. And so we've come up with a method, or basically a standard, which we call the KPPRA, or the K-points per reciprocal atom. And it's given by this equation here. And so it's based on the number of atoms in the unit cell, and then also Ni, or the factors along the reciprocal lattice vectors. And so basically, we're trying to determine what a sufficient grid is based on the number of atoms. And so we'll see this when we start to actually submit the aflow in calculation and how we get this KPPRA. And so in general, this KPPRA, we typically have default values. And so here, for our different libraries, here's what we show. And so for all relaxations, we typically run either 6,000 or 8,000. And for static calculations, we typically increase the number of points, KPPRA. And so typically it's about 10,000, sometimes 8,000 for static runs. And so in here, there's more information such as the potential information and basis set. So here are all the pseudopotential, table of the pseudopotential information. And again, we're using projector augmented wave function potentials. And we designate between PBE, LDA, and things like that. And so I won't go through all of this, but all of the information and basically the default inputs are listed here. And then finally, if you're doing something like DFT+U corrections, so if you have strongly correlated systems, typically D and F electrons, then you typically have a DFT+U correction, so similar to the Hubbard model modeling. And so here are the default parameters that aflow uses. And then one of the last things I want to mention is spin polarization. So in one of the exercises that Corey showed, we had the iron system, or FCC iron, excuse me, or any possible configuration of the iron system. And so we may not know when we get a particular system whether or not we should have magnetism or the magmon flag turned on. And so in general, by default, for the first relaxation, aflow will turn on the magnetic moment. But then if it sees that the magnetic moment per atom is lower than this threshold, then for the second relaxation, basically for a speed increase, we'll turn off the magnetization since it doesn't seem to be important for this particular system. And so that's just one thing to keep in mind for spin polarized systems. And then here is some discussions on the cutoff energies. And I'd say that's probably it that we'll talk about here. So, but again, this is here for your reference. So if you wanted to see some of the standard parameters that we use for this aflow in file. So I'll go ahead and exit out of here. And however, you may be thinking that maybe you want to have some control over what the default parameters should be. And so here, we've been developing what's known as the aflow.rc file, so the aflow configuration file. And so if you're familiar with the terminal, this is similar to your bash.rc file, basically configuring your environment for certain applications. And so this here, you can control the default settings and parameters, default file names. So typically we have file names already predetermined, but maybe you want to change it to something else. And also, if you're running on a particular machine, maybe you want to put some of the default parameters for whatever machine you're working on. So for example, the VASP binary file or the pot car location, you can specify that here. And typically in everyone's, on this cluster, when you install aflow, it'll write out this aflow.rc file, and it's currently hidden in your home directory, but I've also copied it to everyone's exercise directory. So if you'll follow along in the terminal, so we may need to go up a few directories. So by typing the following command, let's go up 3 directories. And so for me, I'm still in the aflow in directory, so we need to go up one more directory. So cd space .. ls. And so now let's go into the second exercise directory. So we'll go cd2 aflow.rc. And if we hit ls, we should see that we have the aflow.rc file in here. So to open it, I'm going to be using vi. So vi aflow.rc and hit enter. And again, the formatting's off just because it's wrapping the text around. So I'm going to type : set no wrap and hit enter. Okay, and so in here you can see some similar things to what we saw in the aflow.in file. So here it specifies the version of aflow. If you want what compression we're going to be using, so by default we're using the XZ compression, but we also support bzip, bzip2, and a few others. Here's for the aflow database, certain paths. For certain analyses, when we write out files, these are the default file names. Again, here, we also have some symmetry files that are written out, and they have a certain name, but you can change that in this file. Scroll down a bit more. Again, if you're using MPI, you can specify the defaults here. For the VASP binary, again, we're on this particular cluster that's using VASP standards. So we've already we've already put this in the aflow.rc for you. That's why when we looked at the aflow in, we were already calling the right VASP binary. Scroll down, the pot car information. And so the pot cars are actually stored on this machine in this shared directory. And so we've specified the path already. Certain parameters, so LDA, PVE, things like that are already specified. The default K paths, or KPPRA. So there's an automatic scheme. So aflow will automatically determine what the K point mesh should be, or if it's a bands calculation, what the K path should be. The KPPRA value. So if you remember, for static or relax, so here it's 8,000 and also 8,000. And then, so there's more default parameters, cutoff energies, things like that. So I won't go through the rest, but all of this is located in the aflow.rc. So what's nice is that you can essentially customize this for whatever workflow you're using. And so it's highly customizable for whatever workflow. All right, so I'll go ahead and exit this file. You can feel free to look at it on your own time, and feel free to play with some of the parameters. Okay, so we're going to exit this file. So if you're in Vim, you hit colon and then Q to exit. Okay, so now that I've shown you what the aflow.in file looks like, let's actually run a VASP calculation. So to do this, we're going to go up one directory. So change directory. So cd space .. /ls to see the directories. And then we're going to go into this energy directory. And so you'll see that it looks very similar to what we did for the first exercises. And so what we'll do is we'll go cd into the aluminum directory, and we have a README. Okay, so but first, let's see how we actually will run VASP with aflow. So I'm going to zoom in a little here. So once you've created an aflow.in, you'll navigate to that directory and you'll run the following command. So you can run aflow --run -d and then the path. So actually, you don't have to necessarily cd into the aflow.in directory, but you do need to specify it here. So this will specify the path to the aflow.in. And some useful commands that you may want to consider if you're running a job scheduler is aflow monitor. So this will essentially log certain resources. So it'll tell you how many resources you're working. And so in case you crash the computer or something, you can use this, and aflow will give you some information on maybe what happened with the resources you were allocating. And so here, if you're using a job scheduler, so for example, PBS or Slurm, so this might be what's in your QSub file or your job script. So you would create a log file, you might run the monitor command, and then finally you would run aflow. And so one thing I want to mention before we get into running the actual system is that as soon as you run this command, aflow creates what's known as a lock file. And so what this does is as soon as you run, aflow makes a lock file. And so let's say you had multiple instances of aflow running, and you don't want to run VASP on the same directory and overwrite your system. And so aflow will look to see if this lock file exists to prevent you from overwriting some certain information. However, maybe you want to run subsequent analyses on these directory. So for example, maybe you did a relaxation, and then you want to run a phonon calculation after, but you have a lock file in there. So here you would need to use the use lock flag. So if you do --use_lock, and then if you specify a new lock file, it'll tell aflow that when it's running to look for this file, and basically you can kind of circumvent this lock file procedure and run the relevant analysis. Okay, so to show you how we can use aflow to basically make this procedure easier compared to all of the examples we did in session 1, we're going to mirror a few of the exercises that Corey showed. So again, we should be in this aluminum directory. And if we type ls, we see the README. And so let's cat the README to see what we need to do. Okay, so to recall what we did last time, we created the aluminum structure in the primitive representation. But this time we're going to use aflow. And we're going to perform one relaxation with no spin. So how do we do this? So first, we're going to use the aflow prototype command. Again, I'll talk about this in more detail tomorrow, but I'll give you the command that you're going to run. So it's actually shown here. So I've highlighted it here, and we're going to type it in the command line together. So the command is aflow --aflow_proto equals, and so this tells us that we want to create an A-flow in for this particular prototype. The label might look a little complicated now, but we'll talk about it later. So it's A_CF4, and keep in mind that this is case sensitive, so you need to make sure that you have the right cases. _225_A dot A, so this specifies a particular decoration, and we want to decorate it with aluminum. And then in this particular case, we have to specify some additional parameters for this prototype. And so again, you'll have to take my word for it, but we're going to put --params equals -1.
David, I think you should be able to do it without it. Try it.
Yes, you can. I guess I was just doing it for completeness, but yes, you don't need params if you want. You can just run this. And you'll see that, like we did before, it creates the subdirectory and then also the alloy system using POP-PBE and then the prototype designation. So what we're going to do is in the A-flow in.
David, there's a question. The question is, what do you mean by decorating?
Okay. So again, I'm kind of getting ahead of myself because I'll be talking about this tomorrow. But basically, a prototype structure is essentially a backbone structure. And so there's no element information when you are looking at this structure. And so when I say decorate, we're basically all of the sites in the particular prototype, we're going to decorate with that particular element. So essentially we're specifying what element is on a particular site. And so in this case, there's only one element, A. So since it's aluminum, there's only one type of element in this structure, and we're specifying it to be aluminum. So I hope that makes sense. Again, we'll see a little bit more, but if there's multiple elements in your system, then you would need to specify more. So for example, if this was a binary, then you would need to specify 2 elements or 2 elements to decorate with. So maybe aluminum and then zinc, for instance. So that's what I mean by decorate. So we're decorating this prototype structure. So hopefully that answers your question. Feel free if you need me to elaborate. But otherwise, we'll talk about it more. Oh, excellent. Okay. So, but again, yes, we'll talk about this more tomorrow. So let's go ahead and navigate into that directory. So cd aflow data /al, and if you hit tab, it'll autocomplete. And if you hit tab again, it'll autocomplete the directory, and then let's hit enter. So we're navigating into this directory. So if we do ls to see what's in the directory, see the aflow in, and just to double check, let's see what's in the aflow in file. So we'll do vi aflow.in, hit enter. Again, I'm going to use my favorite formatting command, so :set no wrap. And we'll see, again, this should look familiar. So, but really I want to go to the bottom. So if you hit capital G, it'll take you to the bottom of the file. And so you can see that with this prototype command, we created the aluminum structure in the primitive representation. It looks a little different than when we did it with Corey because we specified the lattice parameter. And so actually instead of 0.5, it was, I think it was 2 point something. And so, but here, this is taken care of in the scaling factor. So if the scaling factor is negative in this case, it signals a volume. And so this is basically, you can specify it in 2 ways. You can either specify it here with scaling 1, or you can do essentially this form here, and then you can scale it by this volume. Again, I'll talk about this more in the prototyping section. Okay, so we have this aflow in ready to go. So we'll hit :Q to exit from Vim. And so the moment we've all been waiting for, we're going to run aflow. And we're going to see what happens. So to do this, we'll type aflow -- run space -d, capital D. And then the path to the aflow in. So it's actually in this directory. So we're just going to hit dot. And then we will go ahead and hit enter, and you should get quite a bit of output. And so there's a lot going on, and I'm going to go through this briefly. So, but you should see that one of the last lines says we're executing VASP. And so right now the VASP calculation is running. Actually, you know what? I forgot to do something. I forgot to set the relaxation. So hopefully this doesn't mess people up. If you could hit Control-C, that will kill the job. Hopefully this doesn't mess people up. But I guess it's a good opportunity to show you how you can clean your directory and rerun aflow. So hopefully everyone killed their job. If not, please let us know. And hopefully we can help you with that. So, but we want to stop it because we only wanted to perform one relaxation. So if we hit LS, we saw that we started to create some output. So, but let's say we want to perform a clean run and restart this calculation, which we actually want to do. So you can do this with the aflow command line functionality. So if you run aflow -- clean -d dot. So this tells us that we want to clean all of the VASP output and we want to run a brand new aflow command. So if we do this, hit enter, you should see some output. And if you do ls, you should only see the aflow in again. And so now we have a clean directory we can run in. So let's actually go into the aflow in file and make the modification that I should have told you to do earlier. So if we do vi aflow.in, and as I said before, we want to run one relaxation. So to do this, if you're familiar with Vim, to find a certain line or a certain pattern, you can hit / and then type a pattern you want to find. And we want to find relax. So if you type relax and hit enter, it'll take you to a line that contains relax. And so in particular, we want to find the line, actually there's a few. We want this one right here that says VASP run relax 2. So again, as I said, the default behavior or the default setting is to run 2 VASP relaxations via the aflow standard. But here, we just want to run 1. So if you're unfamiliar with Vim, to modify a file, you need to go into insert mode. So you type I, and you should see this insert here. And now you can actually type in this file. So we're going to hit backspace and then 1. And now to exit this insert mode, you need to hit escape on your keyboard, and you should see that the insert mode goes away. And then now we need to save and quit, or actually, before we do that, we also want to turn off the spin. So if we go down a few lines, we should see spin. So it says VASP, force option, spin on, and then remove relax 2. So here, again, we go to insert mode. So we type I, you should see insert. Now you can modify. So we're going to hit backspace and say off. And then for good measure, I'm just going to delete this as well. So the one that says remove relax 2. Once I'm done modifying the file, I'm going to hit escape. And then to save the changes that I made, I'm going to hit :W. So that means save. And then, or if we wanted to save and quit, we could do :WQ. And so if we do that, we're back to where we need. Okay, so now we can run the directory. So again, you need to make sure that you clean the directory with aflow clean. But now let's rerun this now that we have the correct parameters. So we're going to do aflow --run -D and here. Okay, now we should be in business. I guess, are there any questions up to this point? Feel free to say so in the Zoom chat. or if you need to raise your hand. Okay, I'll keep going. And so we can see this last line here, we're running VASP. Okay, so somebody asked a question, how do we save the file on Vim? And okay, so there's a few questions. So while this is running, so to save a file in Vim, you need to make sure you're not in insert mode. And so you hit escape, and then you hit :WQ. I'll type it in the chat. So it's :W is to save. And if you want to save and quit, you do :WQ. So Q means quit and W is save. So this is save and quit. Excellent, okay. And then so the other question was, what was the remove relax to on the spin setting? So again, I think I mentioned in the AFLOW standards running, we typically do we typically have multiple VASP calculations that we run. We typically do 2 relaxations and then perhaps maybe a static and a band calculation. And so I think I mentioned that if we have a spin polarized system, that by default, AFLOW will have spin turned on for the first relaxation. But if after the first relaxation, AFLOW detects that the magnetic moment is very, very small, so maybe we don't need to consider the magnetic moment, it'll actually turn off the spin in relax 2. So I think that's what you mean, because you said remove relax 2, but I think you meant that's for the spin parameter. So hopefully that answers your question. And so again, that's specified in the AFLOW standards paper. But okay, so while this is running, I'm going to scroll back up a little bit to see some of the output. And so this is the AFLOW logger, so it's printing out quite a bit of information. And unfortunately, I can't scroll all the way up. But but typically you might see that we have some symmetry information. So you see inversion and rotation. And so after this session, we're going to be talking about symmetry. And so AFLOW is actually performing a symmetry analysis on this particular system. And then it's also grabbing the pot car information. It's setting up those files to run the VASP calculation. And so while this is running, I'm going to, oh, it's done. Okay, so at least for me, it's done. And so now we're going to see what's in this directory. So if we do ls, we see that there are a few more files than when we did the AFLOW exercises with Corey. We see that there are some files that have AFLOW as prefixes. So these are files specific to AFLOW. You'll see some say P group. So these are symmetry files I'll talk about in the next session. We also have some of the VASP file information. So charge car, OSSI car, post car, and also this lock file. And so you'll notice they're all zipped because we specified the XZ compression. And so again, this is nice if you're running many, many calculations, you want to save as much space as possible. So it's good to have these compressed automatically. And so we'll look briefly at some of the files just to convince ourselves that it did what we wanted. So let's look at the post car. So if we type VI post car, and here for Ridge, so basically this was the original post car. So originally we had to make this by hand with Corey, but AFLOW made it for us automatically. And we exit with :Q. Next, we'll look at the K-points file. So VI K-points. And if we look at this, so here we see that AFLOW automatically made gamma centered and a 20 by 20 grid. And so how did it come up with this? It's because of this KPP array. So again, via the aflow.rc, it was specified to be 8,000. And so what grid gives us 8,000? It happens to be 20 by 20 by 20. And so to exit this file, :Q. We'll look at the in-car, so VI in-car, ridge. Actually, relax is what we want. And so this should look somewhat familiar. So we see that it has some of the preset stuff before, the e-diff, the algorithm, etc. So again, this was automatically created with aflow, :q. And then finally, we want to make sure that, oh, and also we'll look at the pot car, so VI pot car. And if we look here, so this was grabbed from that shared directory that I specified earlier. And so aflow automatically grabbed that and put it in this directory. So :q. And so did we get a similar energy to what we calculated in session 1 with Corey? So we'll look at VI out car, relax 1, hit enter. And we want to go to the bottom of the file. So in Vim, you can hit Shift G, so capital G. It'll take us to the bottom. And if we scroll up a little bit, find that tot10 energy. I think, if I remember correctly, this was about what we had. We had negative 3.74 and change.
David, there's a question about the K points.
Okay, can you specify, thank you. Can you specify the K points grid, or do you need to specify the KPPRA? Good question. Okay, so let's actually exit out of this file and we can take a look. So typically, the default standard is to use the KPPRA scheme that I mentioned. So actually, if we look at the locked file, how this was generated, just to see where it came from. So if we go to the lock file, this is basically that log that we saw. I'm going to, again, use this set no wrap. And if we scroll down, how did it come up with this KPPRA value? It's actually right here. So in the aflow.rc, we specified 8,000. And so aflow determined the correct scheme to get us to 8,000. And that was 20 by 20 by 20. And also in the aflow.rc, we specified that aflow would automatically detect, based on the symmetry, what the K-point mesh we should use. So whether it was monocourse packed or gamma-centered. And so in this case, we used gamma-centered. And so I believe it was because we had the scheme set to auto. But I believe you can specify if you want to force a particular K-point mesh scheme, and then you can also control the KPPRA. So hopefully that answers.
Real quick?
Yes, go for it.
Yeah. To answer your question, Alex, the answer is yes. And I'm gonna maybe I can catch you in a chat or something, but I'm gonna paste a. So if you look in the aflow in, basically there was if you remember, David was going through, and there was a section of the aflow in that had in-car explicit. And so we've created a workflow for where if you want to enter in an explicit file, so can you go to the, yeah, there you go. So all of these settings in here will be put inside of the in-car. So you can do the same thing with the K points. So instead of in-car, you're going to write VAST K points mode explicit, and you're going to comment out all the stuff that says K points implicit mode, where implicit is grabbing from this set of K points file settings. So between, basically in the aflow in, you put, VAST K points mode explicit start and stop, and then you write your K file in there with the explicit K grid you want.
Excellent, cool. Thanks for clarifying, Corey. And yep, no problem. Okay, so with that exercise done, so I think we said this session was going to end at 3 p.m. Central Time, but since I'm the next session and I think I had a little extra time in symmetry, so I'm going to spend maybe 15 minutes in this session just to finish wrapping up, and then we'll go ahead and move on to symmetry. But there are a few other things that I wanted to show. So we want to look at the second exercise that Corey did. So this was BCC iron with spin. So to do this, we need to navigate a few directories up. So I think maybe 4 directories or so. So 1, 2, 3, 4. ls. And so we're back to the energy subdirectory, and we're going to go to 2fe. Hit enter. And so let's look at the README. So we're going to cap the README. So it's going to print it to screen. And so let's see what we're going to do here. So in this case, we're going to create another aflow file for iron BCC. So again, this is what we did with Corey. Looks like I had a typo. It's actually not aluminum. It should be iron. I thought I fixed that, but just follow along with me. Okay, so to generate this structure, we're going to use the same format as before. So aflow -- aflow _ proto equals ACI2 _ 229 _ and then we're decorating this prototype with iron, since otherwise it wouldn't have any elements on it. And as Corey said, we don't need the parameters for this particular case, so we're actually going to leave this off, so you can ignore this. So just type this command here. So if you hit enter, then it does a similar thing where it creates this directory, this alloy system, and then this prototype layer. And now in this case, we want to perform one relaxation with spin. So again, we're going to navigate into this directory, cd aflow data, cd fe tab. Again, you can use tab to autocomplete. Capital A, tab, and then we hit enter. And so now we're in this directory. Again, I'm just going to open this aflow in with vi just to see that it looks correct. And again, my favorite command, set no wrap. Okay, so now we need to modify the file. So again, I'm going to search for the relax keyword. So relax. Again, there are a few. So if you want to find another match, you can hit N and it'll take us to the next one. Hit N again to the next one. Hit N and it should take us to this one here. So again, we want to do one relaxation. So sorry, again, to modify the file, you do insert. So you hit I and you should see insert. Then you can type. So we're going to put 1. To escape insert mode, you hit escape. We're going to scroll down a few more. Somebody asked a question, how can I navigate, find the prototypes library? Excellent question. But actually, I'm going to save that for later. Since we'll be talking about that in session 4, but there is a command to navigate all of the prototypes that we have in aflow. So I'll save that for later. But excellent question, you're thinking ahead. So next we'll modify the spin. So again, you hit I for insert mode, then you type. And actually we wanted this on already. So we're gonna leave it on. And since we're only running one relaxation, we're going to remove this remove relax 2. All right, and so we hit escape. And then we hit WQ to save. And so I'm not going to run this one in particular, just because we're running a little short on time. But I anticipated for this. So if you go up a few directories, so CD, so back to where we were, you should have seen, a pre-calculated directory. So if you do this, CD pre-calculated, and then if you hit tab, it should autocomplete the rest of the path. You hit enter. And if you hit LS to see the contents, you should see something similar to before. And in this case, we'll just see if we have a similar energy as we did in exercise 1. So again, we'll go to the out car. So VI out car, and I'll use tab for autocomplete. Hit enter. And to go to the bottom of the file, you can hit Shift-G. It'll take you to the bottom, and then we scroll up a little bit. And if we look, I'm pretty sure I ran this on this particular machine. And so I don't remember the exact energies, but I want to say it was something like this. So again, this just shows that with one command with aflow, you can generate all of the single input file that you need. And then you run another command to run aflow, and it'll generate all of this information for you. It'll run VASP, and you can get the same results that we did in session 1, but with a lot less of a headache of having to type everything yourself. So hopefully this kind of convinces you how powerful aflow is. I see a few things in the chat, but I think
just answering some questions. It's okay.
Okay, excellent. Thanks, guys. I appreciate that you guys are answering the questions. Okay, so we're going to exit this file, :Q. And then the last thing that we're going to do is we're going to look at this density of states and band structure. So we'll CD up, I think it was 3 directories. We'll hit enter. And I think we need to go up 2 more. 1, 2. ls. Okay, so now we need to go into this directory for DOSBS. So CD for DOSBS, enter, ls. And so here we have the silicon directory. So CD silicon. And then ls to see what's in here. So we'll cat the README. And so in this case, it's the same procedure as before, but we're going to create the silicon structure. But before we do this, I want to show basically some functionality. So in case you want to know if there are extra options that you can add in the command line. So to see this, I'm going to type aflow --aflow_proto. And so you'll notice this isn't complete compared to what we've been talking about before. But if I hit enter, I'll get this output, and this is actually usage information. So if you add some of these flags, you can specify certain things. So if you, for a particular run, if you didn't want to change your aflow.rc file, you could actually specify it for this particular command. And so in particular, we want to run basically a full calculation. So we want to run 2 relaxations, a static and a bands. And so to do this, we can specify this via the command line. So I'll type it here. So it's aflow --, actually I'm going to cat the README so we can see again. Okay, so we're going to use this command first. So aflow --aflow_proto equals ACF8_227_A. We're going to decorate this prototype with silicon. And then I want to specify via the command line that I want to run those 2 relaxations and static and bands. So if I scroll up a little bit, if you see there's a flag for that. So I want to run relax, static, and bands. So I'll add that to my command. So relax, static, bands. And I think it was actually run. Let me double check. Yes, run, relax, static, bands. But then I also want to specify the number of relaxations with relax count. So this here. So go back down, --, relax count equals 2. So hopefully everyone can see this command. So it's the prototype and then these 2 options. And so I'm going to hit enter. And so again, it created this directory. And again, we're not going to run it, but let's just see that it actually did what we wanted. So CD. So somebody was asking, what is the command to see the possible options? So if you just aflow --, aflow_prototype, proto, so just this, and if you hit enter, then it'll tell you the usage information. So it didn't actually run the command, the prototype command, but it told you what options are available with this command. No problem. So we're going to cd them into this directory. And we're going to look at the aflow in, so aflow.in. Again, my favorite set no wrap. And I'm going to search for the relax. So down, down. So next. So I'll hit N, N, N. And here we see that this tells us that we're running relax, static, bands, and equals 2. And that specifies that we're doing 2 relaxations. So actually, if you scroll to the right here, you can see the different possible variants that you could put there. And so in this case, it was this here. All right, so then we'll do :Q to exit. And again, we're not going to run this, but if you wanted to, it's the same command as always, this aflow -- run -d, and then the path to the aflow in. Okay, so then the last thing that I'll do is, again, I pre-calculated this. So we're going to go up a few directories to this pre-calculated. So cd pre-calculated, hit tab a few times to autocomplete. And then we see that we actually have more files than before, because we see original, relax 1, relax 2, static, and bands. So these are all of the VASP output files for all of those different types of runs. So the last thing that we want to do is, this was a bands and static calculation. So let's say we want to plot the band structure and density of states. So I'm going to cat the readme again, just to see the command. And so in this directory, we can use the aflow plotting functionality. And so we can do aflow -- plot band DOS. And hopefully this works without GCC, I think so. Okay, yes. And so what this tells aflow to do is, in this directory, it's going to read the relevant files. So the kpoints file, the DOSCAR, etc. And it's going to create the density of states and band structure plot. So I'm going to look in the directory. So we're in aflow DFT. We're in 4 density of states, silicon, pre-calculated. And if we look at this, we should see a PDF. And if we click on this, we see that this command created the density of states here and the band structure. And so this should look pretty similar to what Corey showed earlier. And so we can see we have silicon, it's an indirect band gap. And so we can see that just, again, with a few commands with aflow, we can automatically generate the files that we had to in session 1. So I think that's it for this particular session. Let me just double check. So I think Corey and Cormac were mentioning in the chat. So I've only briefly highlighted some of the main aflow functionality. And so if you want to learn more and maybe play with some of the parameters, you can look at the readmes here. So if you type, aflow -- readme equals aflow, and I'm going to pipe it to, or I'm going to redirect it to a command or a file. So readme aflow. And then if we open this file, then you should see that this is actually meant a lot of the options that you can run with aflow with respect to DFT calculations. And so here, there's this directory command that we've shown. And so these are all of the different options. And then also at the bottom of this file is an example of aflow in, for silicon in particular. So if we exit, and then the last is if you want to know more about the aflow configuration file, you can do the same by typing aflow -- readme equals aflow.rc. If you hit enter, then it's printing it all to screen, but you can save it to a file and you can see all of the different options that are available.